It's with the help of this model that we can view one of the most principal laws of addition, which we call the commutative law. The commutative law gets its name from the fact that commutative comes from commute, which is to move. So this is the movement law of addition, and it works like this. It says that 3 plus 2 has to equal 2 plus 3. And in fact, if we want to remove ourselves from the specifics of 3 and 2, we can just simply say that A plus B is equal to B plus A. So we can say that 3 plus 2 was that 3 piles and 2 piles, which of course we can look at as being 3 and 2, or we can look at it as being 2 and 3. And in the same way, A plus B we can just write as being 1 pile, 2 piles. Well, I'm not entirely sure how many A is if we're going to keep it abstract, so maybe I'll just put some dots in between and I'll say this is A number of piles. And of course that's going to get us the same total if we combine it with B total piles as we would have gotten if we just simply did B first and then added those A piles to it as well. So it's through this diagram that we can see that we have a commutative law for multiplication as well. A times B is the same thing as B times A, where that word commutative reminds us that all this is the ability to move things throughout that operation. And this has to be true, because if we have A times of B, we can always represent this as a rectangle, where in that first row, we have B instances of these blocks. I don't know exactly how much B is, because we're keeping it general, so I'll just put some blocks and a dot, dot, dot to show that there are some more. But A times of that means that we're going to repeat this entire collection of B multiple times. How many times? Well, A times. So we will always be producing a rectangle that has A instances of B, and through that rectangle, if we flip our perspective, we will be able to view this as instead B instances